Number 10. A student sets up a ripple tank. A ripple tank is a shallow tank of water used to demonstrate wave properties. And there's the apparatus there. The wooden rod moves in and out of the water to generate water waves. The pattern of the water waves is projected onto a white sheet of paper below the tank. The wave pattern appears on the paper as a series of bright and dark lines. The dark lines correspond to the wave crests. The student determines that there are 6 complete waves in 0.12 meters. 1. Determine the wavelength of the waves. Now the wavelength of a wave is the distance between 2 crests, or the distance between 2 troughs, or indeed the distance between any 2 corresponding points. We call that length or distance a wavelength. Now we are told in the question we have a sheet of paper and we have got dark horizontal lines drawn on it, and we're told those dark horizontal lines represent crests. So the distance between 2 dark horizontal lines must be equal to a wavelength. Now these dark horizontal lines are called wavefronts, and it's a good idea to understand how these wavefronts link to our wave that I've drawn here. So how do we get these straight horizontal lines in? Well, let's start off with one wave, and if we draw one wave, then we draw a few waves, and we can see there are the crests, there are the troughs, and there is one wavelength between 2 crests and between 2 troughs. Now if we then now draw horizontal lines through any point at all, in this case the crest, these lines are called wavefronts and they're points of equal height of the wave. If we take away the waves now, we can actually see we've got our series of wavefronts, and this is exactly the pattern we have on our white sheet of paper beneath the ripple tank. The horizontal lines are called wavefronts. The lines represent crests or troughs or any 2 corresponding points. Then do a simple wee question then. The wavefronts represent a water wave moving to the right. Study the diagram above and calculate the wavelength of the wave. Well, we have 10 waves in a space of 12 meters, so the 12 meters divided by 10 waves, and that gives you 1.2 meters per wave. In other words, the wavelength is 1.2 meters, and that's how you set that up. Part 2. 6 complete waves are produced at a time of 0.40 seconds. Show that the frequency of the waves is 15 Hz. Well, the frequency of a wave, well, that's the number of waves that are produced in a second, or produced per second. Or equivalently, it's the number of waves that pass a point per second. And we have a formula to work this out. And the formula is frequency is equal to n, the number of waves, divided by t, the time it took the waves to pass a point, say. So for example, suppose we have 10 waves that pass a point in 2 seconds. Calculate the frequency. Well, that's easy. 10 waves divided by 2 seconds gives you 5 waves per second. The frequency, except we don't say 5 waves per second, we normally just say 5 Hz, where a Hertz is a per second. So 5 Hz and 5 waves per second are exactly the same thing. Part 3. Calculate the speed of the waves. Well, to work out the speed of a wave is the same as working out the speed of any moving body. Distance divided by time. Except when it comes to waves, we have another formula, and that other formula is wave speed is equal to frequency times wavelength. Now remember, the frequency, that's hertz, which is per second. The wavelength is in meters, So if we're multiplying a per second by a meter, we get a meter per second. So the units are correct. Let's see, but does it work intuitively? Well, yes, it does. Suppose we have a wave and it has a frequency of 4 Hertz and a wavelength of 3 meters. Well, what's the speed then? Well, 4 Hertz times 3 meters is 12 meters per second. That's fine. But how does that work though? Well, let's think about this. Suppose we have a 4 Hertz wave. This means it takes 1/4 of a second to produce one wave. And if it travels 3 meters in that 1/4 of a second, well, that's its wavelength, and that's what it will travel in 1/4 of a second. So if it's traveling 3 meters in 1/4 of a second, clearly it's traveling 12 meters in a full 1 second, which is what we expect to get. So it works, the units work, and it works intuitively as well. So what equation do we use then? Do we use distance divided by time or lambda times frequency? Well, that depends on the information we've been given, but very often you can do both. And in our question, we can do both. (10b). The student now places a plastic block in the ripple tank. There, the direction of the water wave is going to the right, and there's a plastic block. And we are asked, complete the diagram to show the pattern of the water waves beyond the plastic block. This question is testing your knowledge of the wave property that we call diffraction. Try to spell it correctly. So when these wavefronts are approaching an obstacle, when they pass the obstacle, they tend to curl round or bend round the obstacle. So when you're drawing our pattern, you have to indicate that. One thing you should note though, although the waves are bending around the obstacle, their speed don't change, their frequency doesn't change, and therefore the wavelength doesn't change. So when you're drawing this pattern, make sure you put the curl on the end and make sure the wavelength is the same after the obstacle as it is before the obstacle.